Raise your hand. Higher, higher, higher. All right. You know, I'm here as your guide to tell you what's going to be on the exam. The exercises might be a clue. Anyway, they're just really good exercises. You work through them. The answer keys are now posted, so you know, do them. I recommend doing them. All right. If there aren't any questions from the last lecture, we'll go on. Okay, this is going to be kind of the second half of electrochemical gradients and potentials, and today we're going to talk about the action potential. And I know you've had some of this before, so maybe this will be a little bit of a repeat, but I think we'll go, you know, maybe a little bit deeper into it today. Good. Okay. So today we're going to talk about permeability, the ionic basis of the action potential. We're going to talk about a methodology called voltage clamp. This is something you will need to know. And how action potentials propagate down the axon. Okay, so in the last lecture we introduced the concept of an electrochemical gradient and equilibrium potentials. So you will need to know how that arises, that you need pumps to set up the chemical gradients, and then selective permeability results in the resting membrane potential. We use Ohm's law to calculate voltage or current or resistance, so you should be able to calculate any one of those from the other two. We introduced the Nernst equation, which we use when we have permeability to one ion, and the Goldman equation that we use when we have permeability to multiple ions. We used a technique that we can refer to as ion substitution experiments. So that's when you change the ionic concentrations, usually outside because that's easier than inside, in order to test the dependence of your mystery current on a particular ion. Okay, so you should be able to sort of design an experiment that tests the hypothesis about ion permeability. We introduced the RC circuit model, so you should all be able to explain and draw a circuit model. That's sort of the basic passive circuit model. And we talked about the passive properties of the membrane. So today, we're going to move on to the active properties of the membrane that result in the signal that we refer to as an action potential or a spike. And this is the primary means of communication between any two neurons, right? Crosses the synapse, so you have an action potential in the presynaptic neuron, you have synaptic release, that causes an action potential in the postsynaptic neuron. And this is the basis for virtually all communication in the brain. Okay, we're going to talk about how that arises and how it really arises sort of from the point of view of variable permeability. So when you have permeability changes, you get an action potential. And we're going to talk about how this propagates along the axon, because the nervous system has some pretty cool tricks about how to do that. Okay, so why do we have action potentials? In the first couple of lectures, we talked about spikes as being sort of a digital signal as opposed to analog signals of the graded potentials. And the reason that you need that is because you need to send signals long distances, and you need to send very accurate signals. So you want essentially an all or nothing spike. It's basically a 0 or 1. It's either there or it's not. And you can encode information in terms of the number of spikes. But the spikes themselves are sort of a unit, all or nothing signal. Okay, and the reason that neurons kind of still have a fundamental problem with this is that axons and neurons are really not very good conductors. They're really not, you know, a metal wire sending electrons down. So they're not very good conductors. So the nervous system has to use certain tricks. And so it's evolved a system of boosting these action potentials. We'll talk a little bit about passive membrane properties. And so the nervous system has to way to maintain that all or nothing signal, because otherwise it would fade away. Okay, so how are we going to study this? We're going to go to the technique of intracellular recordings, essentially. A voltage clamp is an example of an intracellular recording technique. And so far we've talked about intracellular recordings where we have basically two electrodes. So here's your little neuron. So you have one electrode in which so far what we've done is inject current, so pass current through one electrode, and then record the membrane potential through the other. So the membrane is going to change in response to the current injection. So One's the manipulation, the current, and the other is the measurement, the voltage. Okay, so we're going to start there, and we're going to measure potentials to see how they work using this methodology. Okay, so just for the moment, let's go back to our little box where we have the membrane separating the two compartments, and we have an electrochemical gradient, which is set up by differential concentrations of the ions, so 10 millimolar, high potassium on one side, and high sodium on the other side. And this membrane is permeable to potassium and sodium. Okay, but it's not always permeable to both of them equally, right? So we're going to talk about how that permeability changes and how that basically generates the action potential. Okay, so we learned last time that initially the resting potential was dependent on potassium, right? So you change potassium, you can change the resting potential. Okay, so initially the neuron is sitting at its resting potential, which is generally governed by this reversal potential for potassium, or the equilibrium potential for potassium. And you can calculate that from your Nernst potential, from your Nernst equation, right? Okay, and the assumption here is that basically the permeability for potassium is much, much bigger than the permeability for sodium. Okay, and you know, it varied a little bit. It wasn't perfectly linear with the log ratio of the potassium ions. But generally, it's almost entirely based on the permeability to the potassium. Okay, but during an action potential, what happens is this permeability ratio changes. There's an increase in the permeability to sodium, and so that essentially drives the membrane toward the equilibrium potential for sodium. So now sodium permeability overwhelms the potassium permeability. And then that tends to go away, and we'll talk about why that goes away. And we go back to a resting condition where the permeability to potassium is greater than the permeability to sodium. And that's basically it in a nutshell. Okay, so how do we know all this? Let's basically spend much of the rest of the lecture dissecting how we know this is what happens. Okay, so remember last time we performed an ion substitution experiment where we changed the potassium concentration and measured the resting potential. So, you know, low potassium has a certain potential, and then as we increased the potassium concentration in the outside, the resting potential changed. Okay, so we're going to do the same thing, but now with an action potential and sodium. Okay, so what happens if we alter the sodium concentration? So here, we're just going to measure the membrane potential, and here's an action potential. Okay, so it has a peak, and then it has returns back. There's this after, this is VAHP, this is called an after hyperpolarization, because it actually goes down below the resting potential. That's extremely characteristic, and we'll talk a little bit about why that's so, but we're not going to go into so much detail. But basically, let's look at this peak here. So what happens if we lower the external sodium concentration? It gets smaller, right? So here we have a spike. It has some kind of a slower rise, and it doesn't even quite get to zero, and then falls back. Okay? And then when we add the sodium back in, we can get the spike back. Okay. So basically, reducing sodium alters the action potential. What does this tell us about sodium? That it's responsible or not responsible? Responsible. Okay. So when you perform the manipulation and you see a change, you can infer that there's some sort of connection there. Okay. Because if you do the same thing with potassium, what would you expect to happen? Other than the resting potential, you'd basically still expect a spike. The resting potential will probably shift like we discovered before. But because the reversal potential of sodium would be the same, because we haven't manipulated it, you'll probably reach about the same peak. Right? Does that make sense? All right, so let's continue this experiment. That was, one data point. Let's continue this experiment by parametrically altering the sodium concentration outside of the cell. And so that's shown here. So this is sodium concentration on the outside. So as we shift the sodium concentration let's see, let's start with a high sodium concentration. We are around 400 or 500 in a typical neuron. And as we shift it lower, the action potential amplitude gets smaller. Okay, and why does it get smaller rather than bigger? So any change indicates that there's something going wrong with that ion. But specifically, it gets smaller. And the reason it gets smaller, the reason the amplitude decreases with decreasing the sodium amount, is you have to go back to that Nernst potential. Okay, let's write the Nernst potential on the board here. Right, so, can you guys in the back actually see what's on the board here? Not really? Oh, let's see. If I write it bigger, is it just too dark? Too dark? All right, remember your Nernst potential. So E and A equals 58. Don't forget your valence, plus 1 log out over in. Remember? Yeah? You will. Okay. Okay, and so the reason that this changes is because this ratio changes, right? If out gets smaller, that means this ratio is getting smaller, which makes the overall equation result smaller. Okay, so try to think about how you can manipulate the components of this equation and what the result is going to be. Okay, so if E and A gets smaller, then the amplitude is going to get smaller. And it has a roughly linear relationship, just like we saw with potassium. Okay? Now, let's look at resting potential. So now we're going to change the sodium concentration and measure the resting potential. And that's plotted down here. And you can see that there's very little change. Okay, so that goes back to what we were saying. The resting potential is mostly dominated by that potassium permeability. All right. Okay, so experiments like this were carried out by some of the early researchers, Hodgkin and Katz, and they concluded on the basis of this evidence that the resting potential depends on potassium, and the action potential really depends on a transient rise in the sodium permeability. Okay, so just to give an overall summary. This is a lot of words, so this will be in the PowerPoint when you download it, so you don't necessarily have to write it all down. But let's kind of go through it. Okay, so ions flow across the membranes when the membranes are permeable to one or more ion species. You have that electrical chemical gradient. So think about how ions are going to flow given that gradient. At rest, we have the membrane potential that's dependent on potassium. And remember that that is all set up based on those pumps. So those pumps are kind of always working on trying to maintain that gradient. So they're sort of in the background. We don't talk much about them, but they're in the background. And if you mess with those pumps, you're in trouble. Okay, and then an action potential occurs when you have a transient rise in the sodium permeability. So now you have net flow of sodium ions across the membrane. Which way are they flowing? In or out? In. Because there's more out than in, so they're flowing in that direction. Okay? And then we didn't talk about this, but that after hyperpolarization is due to a secondary transient rise in membrane potassium permeability, which we'll get to in a little bit later. But that basically helps bring the membrane back down. Okay, very important. Okay, and when these all kind of go away, they sort of do their thing and then they close, you go back to your resting state. Okay, so just to reiterate, this is what it looks like, transient rise in permeability. But now we're going to ask, well, what causes this transient rise? Some of you know. Yeah.
Opening of voltage-gated channels.
Opening of voltage-gated channels. So it's the membrane potential itself that's causing that change in permeability. Okay. Okay, so major clue, the action potentials occur only when the membrane potential becomes more positive than what we refer to as a threshold level. So this, we'll talk a little bit more about this. So you have to have some sort of stimulus or something else that's driving the membrane over that threshold. Once you do, then you can get these permeability changes. Okay. So This is the mechanism responsible for the sodium permeability. The permeability is a function of voltage. So the permeability of the potassium and of the sodium are both a function of voltage. Okay, but you kind of have to have that initial kick to start everything off. Okay, so how are we going to measure this? Okay, so we've been talking about this permeability, like, we can just look and measure it. It's actually not that easy to measure directly. What we can measure is current. We can measure voltage. Okay, but what we want to know is permeability, which is related to current in a certain way. Okay, but during an active potential, the voltage is changing. And I just told you that the permeability is a function of voltage, but the voltage is a function of current, and the current is a function of permeability. So how are we going to kind of untangle these things? We have to hold something constant. And that's what we're going to do. Okay, so if the voltage is fluctuating over time, as well as the permeability, we need to find a way to hold something constant. Okay, we know from Ohm's law that V equals IR, which we can rewrite as R, the resistance, is equal to the voltage divided by current. Okay, but we're going to start talking about this in terms of conductance, which I actually find a little more intuitive. So electrical engineers talk a lot about resistance, but in terms of an ion channel that's passing ions, I kind of think conductance is a little more intuitive. And this is partly because conductance can be close to zero, but a zero conductance is basically infinite resistance, which I just find hard to think about. Okay, and conductance, increasing conductance means increasing ion flow, which means increasing current. So everything's kind of going in the right direction. Okay, so we're going to start to talk about conductance, which is simply 1 over the resistance, simply the inverse of the resistance. Okay, so instead of R equals V over I, we're going to have G, the conductance, equals I over V. Okay, so to calculate a conductance, we need to know the current and the voltage, but it's difficult if they're both changing. So we're going to use a technique where we can control the membrane potential, V, and simultaneously measure the underlying changes in the current, from which we can calculate the resistance or the conductance. Okay? So the preparation that we're going to use and talk about is this classic squid axon preparation. How many people have heard of this before? Yeah, raise your hands higher. I can't tell. All right, so most of you have heard about this. Okay, so giant squid axons, or we really should call it squid giant axons, because it's the axon that's giant, not the squid. There are giant squids, but we're not using them in the laboratory. Okay, so this is the squid, and this is the axon that we're talking about is part of its defense mechanism, its escape mechanism. Okay, and so this is an axon that needs to be really, really fast. And so it turns out that if you want to be fast, you need to be fat, especially for a squid that's in very cold water and doesn't have, I don't think they have any myelin. So you use this very, very large axon in order to respond quickly to stimuli and get away. Okay, and so this is, let's see. So this is just for relative scale. So this is the axon here. So there's an axon in the middle here, and this is the cross section. So the squid axon is this big red circle. The mammalian axon is about this teeny tiny little dot. Okay, so huge, which makes it very convenient to use in an experiment, right? Okay, and we can also measure ion concentrations in the squid. And this is basically because you can take this axon, and you can take it out of the animal, and then you can get a rolling pin, and you can sort of squeeze the cytoplasm out of this axon, and then measure the ions in it, which is really hard to do in a mammalian system. So that's very convenient. So we can determine the ion concentrations, and these kinds of measurements were the basis for all of the Hodgkin and Huxley cats experiments that we're going to talk about. Okay, so this huge, huge axon means that we can manipulate it in a certain way. So we snip out a piece of the axon, and we can put it in a dish right here. And it's so big that we can stick not one, but 2 electrodes into it. Okay, so, and this was back in the 1950s, I think. And, you know, they had relatively crude instruments at the time. But they came up with this methodology where they would put 1 electrode in the axon on one side, and then a reference electrode in the saline solution outside, and they would use that to measure the membrane potential. Okay, so that's essentially, that's, you know, one of our electrodes that's measuring voltage. And then there would be another electrode that would be the current passing electrode. Okay, and the way that the method works is this. Is let's say we have a command voltage that we want to maintain the membrane at. So say minus 60, which is the resting membrane potential, but that's okay. And we can, let me just note that contrary to this picture, the ends of the axon are actually blocked. So you can control the difference in the ion concentration intracellular and extracellular, right? It's a little misleading in this picture. So we have a known ion concentration inside and a known ion concentration outside, and you can manipulate one without affecting the other. Okay, so back to electrode voltage clamp. So we have a measurement of the membrane voltage here. So that goes through this little amplifier. And we can compare that to a command voltage. So this is the voltage that we want to set our experiment to be. So say minus 60. Okay. Now, if the membrane voltage is different from minus 60, a little high, a little low, this amplifier measures that difference and then sends a signal that says to apply current in such a way that it brings the voltage toward the command voltage. Okay, so you're trying to minimize the difference between the measured voltage and the command voltage by applying a current. Make sense? Okay. So you do that over and over and over again. Okay, so if everything's stable, then you can get it to the right voltage and then not have to apply a lot of current, but usually you have to apply current sort of continuously in order to maintain the voltage. Okay, so you go through this loop. You measure the voltage, compare with the command, inject an appropriate amount of current to get toward VM, toward the command, and then measure the potential and do it again. And you have to do this very, very fast. So you have to have pretty fast circuits to do this. Okay, and so in general, to make the membrane voltage more depolarized, you have to inject positive current and vice versa. Actually, let me correct this. Because this will get confusing a little bit later. So, and I'll correct this in the PowerPoint before I post it. So, to depolarize, I want to inject what I'm going to call negative current. Okay, and that'll make it a little more consistent with what I'm going to show you a little bit later. Okay, so how does this help us measure the voltage-dependent ionic conductances? Okay, well, when those ion channels open, the permeability changes. That's going to affect the membrane voltage. You're going to measure that as a difference between the command and the membrane voltage because the membrane voltage is changing. And then you're going to apply the current in order to bring it back down. So basically you have to apply current in the opposite direction of the way that the voltage is changing. So you're always trying to bring that membrane voltage back to your command voltage. Okay, and so what you do is you measure the current required to do that. Oh, sorry. Oh, let's see. To depolarize the comma. Does that make more sense? Complete sentences. Okay, so we're gonna sorry. Yes, go ahead.
How do you ensure that the response time of the current that's being injected matches what's going on in the cell? Because if it's too fast, then wouldn't it output like before the action potential comes on, and if it's too slow, you're going to miss the entire thing.
Yeah, so generally you can't be too fast, which is okay because you can't design circuits that are fast enough. If you're too slow, then you're always kind of lagging. So the voltage starts to change, and then you're trying to catch up, but by the time you catch up, the voltage is kind of changed, so you need to basically tune your voltage clamp in order to keep up. And so modern systems have lots of complicated little knobs and dials, and it's also complicated by a few other things. But basically, you kind of have to tune your voltage clamp in order to be fast enough to keep up with the fastest currents. And as we'll see, sodium channels are actually quite fast, and so you have to have actually very good voltage clamp. And so there are errors involved in not clamping properly. Yeah, it's kind of an interesting problem. Yeah, but the electrical engineers are on it, and they've designed some really good circuits. Okay, but it's basically, once we get those currents measured, then we can calculate conductance from them. Alright, so let's look at a little bit of history. So these are the sort of two probably most famous people in neuroscience after Ramon y Cajal is Alan Hodgkin and Andrew Huxley. And so they're the ones who came up with this idea of using the squid giant axon, or actually maybe Katz came up with it, but they're famous for using it in a very classic set of papers. So I'm going to show you this little video here. Just because it's just so classic.
By Curtis and Cole in 1940 at Woods Hole. Hodgkin and Huxley first made a plastic cell and mounted it on a platform which could be raised and lowered like a lift. As Professor Baker shows, the axon held by the cannula was then hung in the cell, which was filled with seawater and connected to an external electrode.
I mean, he's like physically.
The internal electrode, which was not attached to the lift, was then placed vertically above the axon, with its tip in the cannula. It was centered with respect to the cannula and axon by placing a small mirror beside the axon, arranged so that a second image at right angles to the first was seen through the microscope. By adjusting the position of the cell, both horizontally and vertically, the cannula and axon were now raised up over the tip of the electrode, which always remained in the same line of sight. Hodgkin and Huxley found that as the electrode entered the axon, a negative potential with respect to the external seawater of about 65 millivolts was obtained. This was the resting potential of the axon, and although its existence had long been suspected, this was the first time it had been directly measured. Moreover, when the axon was stimulated, the action potential did not simply fall to zero during the impulse, but became positive with respect to the outside, shown by the overshoot of the action potential. This important discovery suggested that the nerve membrane, which at rest is mainly permeable to potassium, becomes primarily permeable to another ion during excitation. This other ion is sodium, since if its concentration in the external solution was lowered, the action potential immediately became smaller, by an amount depending on the sodium concentration. If, as these experiments suggest, the action potential was dependent on the passage of ions across the membrane, it was obviously important to measure the currents carried by these ions. To do this, it is necessary to hold the internal potential at a chosen value. This is the powerful voltage clamp technique, originally developed by Cole in America and applied by Hodgkin, Huxley and Katz. This technique requires that an extra electrode, the current electrode, be inserted into the axon. For this purpose, a double electrode was made by winding very fine silver wires around a thin glass capillary. As the wire, which was only 20 microns in diameter, was wound on, it was kept taut, as Sir Alan Hodgkin shows, by dangling a small piece of plasticine on the free end. The finished electrode consists of two entirely separate spirals, insulated where necessary by shellac varnish. While it is inserted in the same way as a simple electrode, the information it gives is quite different. As a change of potential is imposed on the axon, as seen in the top trace, the currents flowing across the membrane are revealed in the bottom trace. The early downward dip, seen on the left, is the transient current carried by the influx of sodium ions, and it is superseded by an opposite and persistent current attributed to the outward flow of potassium ions.
I love that. It's just so beautiful and classic. It's just back in the era when most science was pretty much do it yourself. There were companies building specialized things for you. You had to build it all yourself. So that was kind of cool. Okay, so that's an actual squid giant axon experiment. So we're going to next go through essentially the experiments that they did and talk about those results. Okay, so we're going to perform voltage clamp experiments. And the aim of this is to measure the ion currents that flow across the membrane while we control the membrane potentials. Okay, so we're keeping membrane potential constant and measuring those currents. Okay, and those are the currents, those are what you saw on that oscilloscope. So back in the day, you had an oscilloscope that kind of, you could capture a single sweep or multiple sweeps, and then you took a Polaroid of it and submitted that to the journal article. So if you ever look at old journal articles and you're like, why is the quality of these figures so horrible? That's why, because you're taking Polaroids of an oscilloscope in your laboratory. Okay, but the data. Let's talk about the data. So first we're going to measure currents produced by a squid giant axon when its membrane potential is hyperpolarized. So we're going to try that first. And then we're going to measure currents when it's depolarized. And then we're going to talk about how we can clarify the difference between what we're going to call inward and outward currents. So those two components that you saw on the oscilloscope. All right, so first experiment. And in all of these, we're going to have membrane potential plotted on top. And so this is the variable that we're going to control. And on the bottom is membrane current. And this is the variable that we're measuring, right, in response to the stimulus. So we're at resting, and then we're going to apply a negative stimulus, so negative 65 millivolts of stimulus, and hold it there. Okay. And if we look at the current, what we see is we see a blip in the negative direction at the very onset, and then not much else. Okay, so basically when we hyperpolarize the membrane from rest, not much happens. This inward blip occurs because of the charging up of the capacitor. So what's the capacitor in the neuron? The membrane. So the membrane is acting as a capacitor. Remember your RC circuit. So you've got to charge up the membrane. But basically, there's very little happening in the way of changing permeability. Okay. There's always some permeability that is responsible for that resting potential, but that doesn't change with voltage. Okay. So you don't have to apply any more or less current when you change the voltage because it hasn't changed. So, but that's kind of in the background. We're kind of going to ignore that right now. What you see when you have this change in voltage is the capacitive current, and that's it. Okay. Now, when we apply a positive current, which is what they were doing in those experiments, we get a very different response. So we apply a positive 60 millivolts, so it goes from negative 65 to 0 millivolts. Okay, 0 is relative to the outside. That's our reference voltage. And what happens? We have now that blip early on, but in the opposite direction. And then we have a transient, what we're going to call inward current, and a delayed outward current. Okay. So these terms, inward and outward, you will need to know this because this is convention. And this inward current is by convention always expressed as a negative current. And this is why I wrote down this. So this is the negative current. And as you'll see, this is responsible for depolarizing the cell. So that's always a little point of confusion. And it has to do with just the conventions of voltage current. Okay, so just kind of memorize it. Outward is positive, inward is negative. Okay. So we have this sort of strange current response. All right, so let's do some more manipulations. Let's give it, depolarize it, but at different amplitudes. Okay, so let's start small. So we go from rest to negative 26. Okay, so from about negative 65 up to negative 26. And we'll measure the current, and now we measure a little inward current and a little outward current. If we go from negative 65 rest to 0, like we just saw, you have that inward followed by outward. If we depolarize even more past that 0 point, we get now kind of a smaller inward and a bigger outward. So now the inward and the outward are kind of doing something different. And then a larger voltage change. And now we don't have any inward current and an even larger outward current. And we're going to ask, well, why is there no inward current here? Come back to that. And finally, we have an even larger step. So we go from minus 65 to positive 65. So that's a jump of 130 millivolts. And we get all outward currents, but now it has this kind of strange little blip at the beginning. Okay, so first of all, can anyone explain what's happening to the inward current here? What ion do you think is that being carried by? Sodium or potassium? Sodium. Okay, so what we were just listening to. Okay, so what's happening here? Why is it 0 here, and then maybe a little outward blip here?
That might be like the point at which you open voltage-gated potassium channels after the action potential.
Okay, so one answer is that is the point at which you're opening voltage-gated potassium channels, so kind of countering the sodium channel, you think? Anybody else? What's the reversal? What's the equilibrium potential for sodium? Have you done your exercises? No. Yeah? Anybody? 50-ish. Let's call it 40 to 50-ish, depending on exactly what the concentrations are. But it's on that positive end, just like potassium is negative 50-ish something. Sodium is always sort of 40-ish, 50-ish in the other direction. Okay, so around negative 52, well, this suggests that it's actually at negative 52. So what this says is that when you're at your equilibrium potential, which way are ions flowing? Inward, outward, or nowhere? Nowhere. Okay, so when you're on one side of your equilibrium potential, you're going to have inward flow. When you're in the other side, you're going to have outward flow. So this little blip here is because sodium ions, instead of flowing into the cell, are now flowing out of the cell, just a little bit. Okay, there's not a big difference between 52 and 65, but it's enough that you flip the polarity of your current. Okay, what about this component? This just gets bigger and bigger and bigger and bigger. Let's think about this. Let's come back to that. Okay, so what did we learn from these experiments? We learned that the initial response of the axon, okay, there's a redistribution of charge that's responsible for that capacitive current. That's just charge kind of bumping up against the membrane until it reaches its capacitance. So it's capacitive. Okay, and that's why you get that transient blip. It happens really fast. Okay. When you're hyperpolarized, there's very little current that flows. When it's depolarized, we get a very interesting set of responses. We have, after the capacitive current, we have an axon that produces an early, rapidly rising, inward, negative going current. Okay. And then it's followed by a more slowly rising, late, delayed outward current. Okay, so let's kind of split those into two components now. Okay, and we'll call them early and late. Very descriptive. Okay, so we're going to measure the amplitude of the early part of the response and measure the amplitude of the late response. So the early response started, let's see, from -26. So let's just back up just a minute. When we hyperpolarize, we got no currents at all. Okay, so that's going to be 0. Plot that as 0 here. As we depolarize from rest, we get a fairly small response in the inward direction, and then it gets bigger, and then it gets smaller again, and then it gets 0, and then it gets positive. So that's shown by this curve right here. Okay, so you have a small inward current that gets bigger, and then smaller again, hits its equilibrium potential, and reverses sign, and continues to get bigger in that direction. Now the late component starts off outward and just gets bigger. Okay, so a plot like this, that is plotting the membrane current at a particular time point versus the membrane potential that we're holding it at, is the voltage response of these currents. Okay? And what this implies is that, if we sort of assume that each of these components is because of a different set of ion channels with particular properties, we can see that both of these are voltage dependent. Okay? But the way that the ions flow into or out of the cell depends on the equilibrium potential of that particular ion. And that particular ion channel has permeability to a particular ion, that particular ion has an equilibrium potential, and so whether ions flow inward or outward depends on the equilibrium potential. Okay, but they're both voltage dependent. Okay, so far we found that the current can be separated into these early and late components. And we've looked at the properties, the voltage dependence of these early and late components. And just sort of repeating the same. There's nothing in the negative direction, but changes when you have depolarization. And a more positive potential currents flow and change in magnitude. Okay, so we think that early component is being carried by sodium. So how can we look at that? So we can go back and basically do the same experiment, the ion substitution experiment, and manipulate sodium to determine whether there's an effect on the inward current. So what happens? So initially, we have 460 millimolar sodium in the external solution outside the cell. If we reduce the sodium to nominally 0, what happens? Well, not much happens to this late component, but that early component is radically changed. Now we have, instead of an inward current, we have this little outward flip. Right? Okay, so we know sodium is responsible. And when we add it back, we get it back. It's always good to return to your control to make sure that your experiment is good. Okay, so what we found is that in low sodium, that early inward current reverses its polarity and becomes a small outward current. Okay, and so we can conclude that when sodium is present in the external medium, that this is due to sodium entering the neuron. Okay, so another way to kind of try and separate these currents is to use pharmacology. So we mentioned in one of the earlier lectures that these ion channels are often a target for various kinds of drugs. And a lot of those drugs are based on toxins. one of which is the fugu toxin, tetrodotoxin. And so tetrodotoxin is very specific for voltage-gated sodium channels. Okay, so when we add tetrodotoxin, we can show that this inward current is much reduced. Okay, but it leaves the outward current basically untouched. Conversely, a drug named TEA, tetraethylammonium, is specific for potassium channels. So you apply TEA, you can block that late component and leave this early component intact. And this is what working neuroscientists do all the time. When you're trying to investigate currents, it's very handy to have a little toolkit of drugs or toxins that allow you to hone in on just one component. So you can block all of the ion channels that you're not interested in, and then you're only left to measure the ion channel that you are most interested in. Okay, just summarizes, TTX blocks the inward, TEA blocks the outward, and the conclusion from that is that because we know TTX blocks sodium, so sodium must be inward, TEA blocks potassium, so the late outward must be potassium.
Does TEA block the leaky channels?
Not much. No. I'm trying to remember. The leak channels, for a long, long time, people didn't know what the leak channels were. And so it turns out that a lot of them are quite a different channel. Whose name I can't remember. But you can assume the TEA blocks the voltage gated channel. So we'll talk a little bit more about channel families in the next lecture on Thursday. Okay. So we've learned that the conductance of a particular ion is voltage dependent. Okay, and mostly we've talked about measuring the peak, but we know that they also have a time course. So there's a kinetic component to these ion channels in their voltage dependence. Okay, so let's start to look at that. So initially, we looked at a depolarization, and we saw this capacitive current, transient inward current, delayed outward current. Okay, but now let's try and separate them into their different components. Let's pretend that we've applied drugs and that we've measured individual currents. What's shown here are the voltage steps. So these are different sets of voltage steps. This is the total current, so just like we saw before. But now imagine that you've applied your TTX or you've applied your TEA and you've measured the current. Okay? And the current is a direct reflection of the conductance. So let me write down my thing. This is actually in an earlier note, but let me write it down right here. So current is equal to the conductance, okay, which we just talked about as being voltage dependent, times Vm minus the equilibrium potential for that ion. So if you can measure the current under these controlled circumstances where you're blocking all of the others, and you know Vm and you know the reversal potential, the equilibrium potential, you can infer the conductance. Okay, it's a direct reflection of that. All right. So that's what we're showing in the bottom two panels is this calculated conductance for sodium or for potassium when you apply these different steps. So let's look at the first one. So we apply a voltage step. We're getting a small inward and outward. And now we are showing the conductance change over time. So time is on the x-axis. So the conductance increases and decreases. You can see this better here. So when you have a larger voltage, you have a larger conductance, and then a larger conductance, and then another conductance, and an increase. And there are a couple of things that you want to notice. The conductance is increasing here. Okay, and that's different from that current. Remember, that inward current is sort of small, gets bigger, gets smaller, and then reverses. Because the current is dependent on the relationship between the voltage that you're holding the cell at and the reversal potential, right? So as the voltage gets closer to the equilibrium potential, this gets closer to 0, so the current gets smaller. As this voltage gets farther away from the equilibrium potential, it gets larger, okay? But it's all dependent also on the voltage dependence of whether those channels are open or not. Okay, so for sodium, we can infer this from this amplitude of the conductance. So the conductance increases because the permeability is voltage dependent. So this is what we call the activation curve. So this is conductance, which directly reflects the permeability. So around resting potential, the permeability is very, very low, and then it increases with voltage until it reaches some saturation point, maximal point. Okay. So the conductance is voltage dependent. So this is following that curve. And then the amplitude of the total current for the sodium depends on the difference between the voltage, the membrane voltage, and the equilibrium potential. Does that more or less make sense? Let's look at the potassium, because the potassium is maybe a little easier to understand. Okay, so let's look at the conductance for potassium. Okay, so the conductance for potassium starts off, it's delayed in time, but the amplitude increases simply with voltage. Okay? And so it has a very similar activation curve to the sodium. Okay? But the currents look really different, right? So the inward current starts small, gets larger, gets smaller again, and then reverses eventually. Whereas the potassium component is always outward. It starts small and then gets bigger and bigger. Let's go back to this graph. Okay, so again, this then is the potassium component. So it opens at a certain voltage and then gets bigger and bigger. Okay, and it's actually for two reasons. The current gets bigger because, oh, chalk. Because the permeability is increasing, but the current is also sensitive to the change between the voltage and the equilibrium potential for potassium. Anybody remember what the equilibrium potential for potassium is, roughly? 75, yeah, depending. It's like negative 75, right? Negative 65, negative 50. What we first calculated, negative 58. So somewhere around there. So it's basically down here at rest, okay? And then as you depolarize the membrane, you get farther and farther away from that equilibrium potential. So both of those things are increasing. The conductance is increasing. Let me rewrite this for potassium. So it's exactly the same equation for the potassium. G, K, V times V, M, E, K. So remember, EK is roughly, let's call it like negative 60. Okay, and ENA plus 40 or 50-ish, little volts, somewhere around there. Okay, so GK is increasing with voltage, and this component that we often refer to as a driving force is also increasing with voltage, right? So as you're moving away, if the equilibrium potential for potassium is here, and you're moving away, you're increasing that driving force. You're increasing the desire of those potassium ions to flow across the chain. Okay, so this has a very simple, both of those components are increasing. The INA is complicated because at rest, those channels are closed. So you have the conductance, as you're increasing the voltage, is increasing, okay? But the ions, the ion flow is sensitive to this difference. So initially, you're really far away from the reverse potential for sodium, which is here, right, this crossing point. So initially, you're far away from the reversal potential, but your conductance is really small because you haven't really opened that very much. As you move the membrane potential more depolarized, the conductance is increasing, and even though you're getting closer to that reversal potential, the conductance is much bigger. Okay? So you kind of have both of these effects. And that's why this response, this current response, gets bigger. Okay, and it's still inward because we're on this side of the reversal potential. So ions are flowing into the cell. Okay. Now, as you depolarize more, you're having a larger conductance. It's more permeable to sodium, but now you're getting really close to that reversal potential. Okay, and so the current goes to 0. When these two things are equal, the current is 0. There's no flow. And then as you depolarize even more, this flips sign. Okay, so now you have a large conductance, but you have a sign flip here, and so now you have an outward current. Okay, does that make sense to everybody? Kind of work through this in your mind. The book is pretty good about talking about this. Yes?
So the conductance of potassium then stayed the same throughout?
Let's move on. Let's see, how are we doing? Okay, let's move on, and we'll talk a little bit about how those conductances are changing in time. Okay, so I started to go on to, so this describes this equation that I was talking about here. Okay, so let's talk about those kinetics. Okay, so those ion channels, they're proteins, they have a particular voltage response, and we just showed you that those activation curves are basically the same for the voltage-gated potassium channels and the voltage-gated sodium channels. But there's a really major difference in the timing of those openings, right? So the sodium conductance opens and then closes, and we call this actually inactivation. So channels can be open, they can be closed, or they can be inactivated. So those are sort of three states. We're not going to go into detail in channels, into channel states, channel kinetics, but it's classically important that these sodium channels inactivate. They close and they won't open again. Okay, and so that's what accounts for this transient increase in the sodium permeability. So remember the very beginning we talked about a transient increase in the sodium permeability? That's why. Because those channels have the property of inactivation. The the potassium conductance, on the other hand, is more slow to open, but once it's open, it stays open. As long as the voltage is held constant at a particular point, so remember that activation curve, it will stay open as long as the voltage is held there. Okay, so one way to talk about this is that these potassium channels don't inactivate. They're non-inactivating. That's what we put it. Okay, so that's the kinetics. So the activation curve is sort of a steady state function or a peak function. Sodium currents inactivate, potassium currents do not. And they have kinetics that are based on their open states, closed states, and inactivated states. Okay? And different ion channels are going to respond with different kinetics to exactly the same voltage. Okay? And we're talking about sort of two particular species here, the voltage-gated sodium channels and the what they call the delayed rectifier potassium channels. But there's an enormous variety of different ion channels that all have their own particular kinetics. They activate differently, they inactivate differently, they have different voltage dependencies. And so that's where a lot of the variety in physiological function comes from. Okay, so we've been talking a lot about voltage clamp experiments. And that's because it was really convenient to be able to hold that voltage steady. Okay? But during an action potential, the voltage is fluctuating, right? Normally the voltage is going along, this is what the cell does on a normal basis. You have these big fluctuations. And so we have this sort of feedback loop that the currents affect the voltage affects the permeability affects the current, and the current affects the voltage. Okay, and so that's what's going on during an action potential. So all of those things are happening dynamically. Okay, but we can use the data from our voltage-gated experiment, our voltage clamp experiments, in order to build a model. And if we do that, we can construct a model and calculate exactly what the conductances would look like given the time-dependent changes in voltage. Okay. And we're not going to talk a lot about doing that, but there's a lot of computational modeling that does exactly that a lot. And so this is basically what it looks like. So the sodium conductance doesn't look that different from what we just showed you, that it increases transiently and then it decreases. Okay. Partly due to that inactivation, but also partly because the voltage goes up and then the voltage goes down. Okay, so when the voltage goes back down, you sort of shift left on that activation curve and the ion channels close, or they don't open anymore. Okay, so that's transient, but it looks pretty similar to what we've found in the voltage clamp experiments. Now the potassium looks quite different. You'll notice that the potassium conductance increases, and it increases with a bit of a delay, like we saw before, and then it decreases again. So why does it decrease? Are they inactivating? No. They're also responding to this decline in the voltage, so they're also shifting back down their activation curve, and they're closing, and they're not opening. Okay, so both of these things are transient. So you have this increase in the sodium permeability that depolarizes the membrane. When it inactivates, you have inactivation of the sodium, so that basically allows it to fall back down. But you also have this delayed activation of potassium. Now potassium is going to flow out of the cell, right? Sodium flows in, potassium flows out. Having positive ions flow out of the cell makes the cell hyperpolarize, right? So it's basically losing charge, is another way to think of it. And so the opening of these potassium channels causes a repolarization of the membrane. And in fact, they stay on a little bit longer. And because the reversal potential, the equilibrium potential for potassium is actually a little bit below that resting potential, you get this negative undershoot of the action potential. So you kind of have to think about this as this sort of dynamic system where things are opening and causing voltage changes. The voltage changes are causing things to open or close, and then that's having an effect on the voltage. So it's not a simple thing. All right. So how do we kind of get that all or none effect in the reason that action potentials are all or none when they reach that threshold is because there's a positive feedback loop, right? So we said that when you open sodium channels, sodium ions rush into the cell. Positive ions rushing into the cell causes it to depolarize. Depolarizing causes more sodium channels to open, and so on. And so you have, an initial depolarization, open the sodium channels. You have sodium current that causes more depolarization, and so on. So we have a positive feedback loop. Okay, and so basically you kind of hit this point of no return, and that's where this concept of threshold comes from. There's a point where the voltage is so positive that you start to get these sodium channels open more and more and more and more. And that's finally you have a membrane that is mostly permeable to sodium. Okay. So then it shuts off eventually because these sodium channels basically stop. If they're inactive, they can't open anymore. Even if you're depolarized, they still won't open. And that's kind of the difference between inactivated channels and closed channels. Closed channels are not passing current, but they're ready to, right? So if you change the voltage, they're like, woohoo, okay, we're open. Inactivated currents say, no, I'm not going to do anything. You know, you're knocking on the door, I'm not going to open. Okay. And so the inactivation is actually really critical to basically short-circuiting this positive feedback loop. And then you kind of get into a negative feedback loop. So you depolarize, you have this delayed opening of potassium channels that cause a potassium current, that causes a hyperpolarization. It pulls the membrane down below that threshold membrane potential and stops the cycle. All right. So if any of this is unclear, if you go to the textbook website, you should be able to access some of the little simulations, some of the little videos that they have. They're kind of helpful. It's nice to have, have a little passive learning there. Okay, so, but I'm not going to do it during the lecture. Okay, so Hodgkin and Huxley just had a tremendous impact with their understanding of how nerve cells work through these physiological recordings. And this is really the basis of all, biophysical, mathematical models of neurons and brains. And so these are referred to as the Hodgkin-Huxley equations, the Hodgkin-Huxley model of sodium channels. We're not going to go into great detail about it, but basically you can take the RC circuit, the sort of passive RC circuit, and instead of having just the potassium, what we often call the leak channel that's responsible for the resting potential, you have now these voltage-dependent conductances. And so this is shown as like a little resistor symbol with a little arrow through it. And so that implies that there's a voltage dependence. Yes?
So, I remember when we learned about this before in high school, they talked about how on.
You learned this in high school? Really? They teach this in high school? Oh, you learned it in high school. Okay.
Oh yeah. They were talking about how at a particular potential, that's when everything opens. But based on what you're saying, it seems like these voltage gate channels are more sensitive to transient changes in potential rather than opening at the same time. And because the active potential is at a certain point, you get that sort of that beat, the fast feedback really beats the slow one, right? And then everything kind of opens.
Oh, you're way ahead of us. Yeah. So he's. Let me see if I can summarize what you're commenting. So the comment is that we talk about this threshold, but it really seems like it's kind of dependent on a lot of aspects of the sort of the recent history, maybe, of the membrane. And so that is probably a very advanced topic. And so in my laboratory, actually, we've been looking at. So, we kind of say threshold is this, voltage. And we sort of draw a flat line as if, above there you spike and below there you don't. And it's really a soft threshold. That depends on the recent history of the neuron and the state with which these ion channels, the state in which these ion channels are sitting at a particular point. So it's quite dependent on the past history of the neuron at any given time. Yeah, but for the purposes of this lecture, we can think of it as a voltage threshold. A cell sitting at rest, and then it has some stimulus that causes the membrane voltage to change, and then you have changes. And so if those are the conditions, then the threshold is actually really replicable. You can determine the threshold under those conditions actually very precisely. It's when you have ongoing activity in a normal neuron where you have spiking and you have synaptic inputs that things get very complicated very quickly. And there are interesting consequences to that we're not even going to get close to discussing. Okay, So this is just our slightly more advanced RC circuit. And let me just introduce for now. We're going to pick this up a little bit in the next lecture. We haven't finished today because we still need to talk about axon propagation. Okay. So how do we get from point A to point B? You need to get to those presynaptic sites. You need to get from your head to your toe. And how do you do that? Okay. So in the next segment of the lecture, let's just introduce this idea of passive current flow in the axon. Okay? So let's take an axon and we're going to stimulate at a particular point. Okay, so now we're back to injecting current and recording voltage. Okay? So here we're going to inject current through one electrode and record through another electrode. So our current electrode is at a particular spot. And then we're going to, magically have this array of recording electrodes. Okay. So if we record at the same spot where we injected, we get that nice sort of passive response. Remember, there's the time constant of charging up, and then the amplitude of the voltage that's determined by Ohm's law. Remember? Yeah? Okay. And so that's what happens if you're recording at the stimulation site. As we move away from the stimulation site, you can see that the amplitude of this response gets smaller. Okay? And that's because the current that's entering here is flowing down the axon. But you're losing a little bit of current back out the membrane. So the membrane is always a little bit, what we're going to call leaky. Okay? There's always a propensity for a little bit of current to kind of leak out of the membrane. So if we measure this amplitude of this step, we'll find that it has a peak right at the point of stimulation, and then it declines as you move along the axon. So the x-axis here is the distance along the axon. And so it declines. And so that's this decline here. Okay, so that's what happens with graded potentials, right? And that's why we don't want to use graded potentials to travel long distances, is because the signal fades away. Okay. All right, so let's just take a moment, and I'll come back to this at the beginning of the next lecture. We can come up with an equation to describe the way that this decay occurs. And we're going to introduce this idea of lambda, which is known as a space constant, or a length constant. Okay, and so this is a description of how the voltage decays, and it happens to decay in an exponential manner. Okay, so it decays in an exponential manner. When it reaches roughly 1/3 of its initial value, we're going to define that as our length constant, lambda. Okay. In the squid axon that we've been talking about, lambda is about 1 millimeter. Okay. In mammalian brains, it's a lot smaller. So we really have to deal with this problem of this loss of current. Okay. And so the equation for this kind of loss is the Vx, where x is the distance from the initial point, equals the initial voltage response at the site of stimulation times e to the negative x over lambda. Okay, and I think we'll just stop right there.